All right, let's continue on with our circles unit, and we will today talk about special segments in circles. So for our first property here, we will be discussing chords. Remember that a chord is indeed a segment, so I have two chords intersecting here. So when those two chords intersect, I have that those segments will have a special relationship. So what happens is I'll end up taking the product of the two lengths of those intersecting chords. And again, the product will be multiplication. So I'm going to drop that in over here. So I have the products. A times B is equal to C times D. And those are my chord lengths from the diagram here. You can also think about taking a part times the part is equal to part times part. So chord length A times the other part, chord length B, is equal to the length C times length D. So let's try an example below. I have my lengths 8 and X, and that will equal the product of the 6 and 20. So I've got my work over here to the right. So 8X equals 20 times 6. My next step, I will multiply through 20 times 6. 8x will equal 120, and if we divide both sides by the 8 in order to isolate my x value here, I will solve to get x equals 15. So 15 is my final answer. Let's take a look at our next one. Again, I have two intersecting chords, those segments in the circle. I will take their product, so 12 times x will be equal to 4 times 18. So 12x equals 4 times 18. Our next step, we'll multiply this 4 and 18. 12x equals 72. And if we divide both sides by x, my final answer, I will solve for x equals 6. And that's my first property. So again, when two chords intersect, I will take the product of their side lengths and set them equal. For our next property, we will be looking at secants. All right, so now I'm talking about two secants. Again, a secant is going to be one that goes through the circle again and touches at 2 points. So I've got touch here and here. And then my other secant goes through the circle here and here. So this one also has a special relationship. So what I will find is that A is going to be multiplied times A plus B. So again, I have my outside A will be equal to A plus B. So I may even make a note here that this full length is the A plus the B. So A times A plus B is equal to C times C plus D. And also on this secant line here, I can combine these just to clarify for myself that this total length will be the addition of C plus D. So you can also think of this as actually taking the outside times the whole is equal to the outside times the whole. So again, I have the outside here, which is A, times the whole length, which is the A plus B. And then my other segment, this secant here, I have the outside part C is equal to the whole, which is C plus D. So let's take a look at an example. For this first one here, I will be solving for y, and let's go ahead and make a note of the total length. So I have an 8 and a 4, so if I were to sketch in my total, I should have 12 here when I sum 8 plus 4. And then for this other length, I will have y plus 3 for that total. So remember, I'm going to take outside times the whole thing. So 4 times 12 will be equal to the outside, which is 3, times y plus 3. So you can see that in my equation to the right. Our next step, since we do have the parentheses, we must take that order of operations first. So distribute the 3. So I have 3y plus 9. And then I multiplied the 4 times 12 to get 48. Continuing through, I'm still trying to isolate y. So I'll move this positive 9, take the inverse operation of addition here, which would be subtracting 9 from both sides. So now 3y equals 39. Divide both sides by 3, and I will solve for y equals 13. For our next example, let's combine to find our whole length. So I will have again a 12 here, and then the length y plus 6 for this other piece. So let's take the piece, the outside piece, times the whole piece. So 4 times 12 will equal the 6 times y plus 6. With my parentheses here, let's go ahead and distribute. So 48 equals 6y plus 36. Isolating to get y, I'll subtract 36 from both sides. So 12 equals 6y. And my final step, dividing both sides by 6, I will solve for y equals 2. Final answer. So we've got one more property. Our last one deals with actually taking a tangent line and a secant line. So a tangent line, recall, will touch the circle at only one spot, and a secant line will touch that circle at 2 spots, go through the circle in 2 places. So when a tangent and a secant intersect, we again find a special relationship between them. It's basically the same relationship as in number 2. So let's take a look. I will end up with taking a squared equals b times b plus c. So I have a here, and then for this total length, I end up with this addition here. So again, it's just like in number 2, I'm taking the outside times the whole equals outside times whole. In this case, the a happens to be the outside and the whole. So it's just multiplied by itself, in which case we get this squared term. So again, a squared equals b times b plus c, outside times whole. So let's take a look at our example. So my outside piece, this is our tangent line. I will square the 9, and then let's find out below, just to write in that total length, I have x plus 3 for the total length. So for my work, 9 squared equals 3 times x plus 3. Again, with the parentheses, we must distribute. So 81 equals 3x plus 9. Subtract 9 from both sides. 72 equals 3x. Therefore, x equals 24. And remember, any of these you can go back to actually substitute in and check your work. So if I were to check my work, I have 9 squared, and that should be equal to, if I have x plus 3, then I know that if x is 24, this should be a total of 27. And if I look and take 81, is that indeed equal to 27 times 3? And if you do your work here, you will find out that 81 equals 27 times 3, which is also 81. So check. Yes, my work is complete and correct. Always, you can check your work. Do not hesitate to substitute in back for that variable. This will wrap this section for our special segments.